Number 20 here is a really tough problem, guys, but I assigned it because I think it's a really interesting application of what we're doing here with optimization. So just getting the diagram set up for this is confusing because there's a lot of words going on right here. So what's going on here, guys? We've got an injured hiker and we got to get him to a hospital. Now there's a road that the hospital is going to be located on. So I'm going to go ahead and draw the road right here and then put a dot at this point right here, and that is going to be our hospital. Now the hiker is well off the road. So we're going to put the hiker up here out in the wilderness somewhere. And this four-wheel drive vehicle is trying to transport the hiker to the hospital. Now, here's what it says. From a point that's 30 kilometers from the nearest point on a straight road. So the nearest point on the road to the hiker is going to come straight down here, and it's going to make a right angle with the road itself. So that distance right there, guys, is 30 kilometers. So basically we're saying that the hiker who's injured is 30 kilometers from the road. That's the nearest spot. Then what they're telling you is that the hospital is 50 kilometers down the road from that nearest point. So this distance down here on the bottom is going to be 50 kilometers. Okay, so that's where we're at here, guys, and we are trying to get our injured hiker from point A to point B as quickly as we can, because obviously the person is injured and we're trying to get the medical attention. Now, how we get there, though, is really, really interesting. It's very, very tempting to think that that the fastest way to get from point A to point B would be on a straight line. And if we were flying the person there, let's say in a helicopter, that would definitely be the way that we would get from point A to point B. However, what's interesting, and I think maybe realistic about this, is that this person's out in the middle of nowhere. So we're taking a four-wheel drive vehicle right here that doesn't travel at the same speed through the woods that it can travel on the road. So what they're telling us is happening in this problem right here, all right, is that we're going to take this hiker injured in the four-wheel drive vehicle on kind of a goofy route here that's actually going to go at an angle like this and then pick up the road at a point right here and then move to the left down to the hospital that way. So we are going here and then we are going here, and it's probably some kind of combination of routes here that's going to get us to the hospital not in the shortest possible distance, but I want you guys to read this carefully. We are trying to minimize time. And again, I don't think a whole lot of paramedics, firefighters, rescue personnel are doing calculus when they're out there saving people, but it is definitely true that time is of the essence with an injured person. You need to get them to the hospital as quickly as possible. So we don't care about the shortest possible distance, and we don't really care about fuel economy or anything like that. We are trying to minimize the time that it takes to get that person to the hospital. Okay, so there's basically two legs of this journey right here, guys. I'm going to call this leg 1 and then this leg 2 for where it is that we need to now figure out the time it's going to take for leg 1 and leg 2, add those times together, and then minimize that overall value. Okay, so here we go. Now the question is asking us, how far down the road should the vehicle aim to reach the road? So I think what we're really doing here is looking for a value here that we're going to call X. And I think if we can find the value of X, that's basically the answer to our problem. So that's what we've got right there. And what I see here, everybody, let's take a look here, is we've got a distance right here problem. It's basically a right triangle with 30 kilometers right there, X kilometers right over here, and then an amount that I'm going to call D1. And I'm going to set up the Pythagorean theorem here, guys. X squared plus 30 squared is going to equal D1 squared. That's confusing because it's got a subscript and a superscript right there, but okay. There we go. And so that's that distance right then. And I think we could say then that D1 is going to equal, if I was solving that now, I would do the square root of both sides. It'd be the square root of X squared plus 30 squared is going to be 900. Okay? And that is distance 1 right there. However, we are not trying to minimize distance. We're trying to minimize time. And so to do this, I want to make sure that everybody knows a very basic equation when we deal with something in motion right here. Distance is equal to rate times time. That's one of those equations that unfortunately I think a lot of calculus books and teachers like me assume that you guys know from basic science classes, and maybe that's not necessarily the case. Anyway, if distance is equal to rate times time, then what's going on right here is that on leg 1 here, distance, all right, let me write this out, d1 is equal to rate 1 times time 1. Well, d1 is what we just found right here, guys. The square root of x squared plus 900 is equal to rate 1. Now, let me stop right there. Rate 1 is how fast this vehicle can move through the terrain. And I'm reading right here, guys. If the vehicle can drive at 30 kilometers per hour over the terrain. So rate 1 is going to be 30, and T1 is what's unknown here. So now, if I solve that for T1, guys, T1 is going to equal the square root of x squared plus 900, all divided by 30. Now, I'm nowhere close to my answer here, guys, but that's something really important. That expression tells us the time that it's going to take to get from the injured hiker to the road on this little angle right here. Okay, now I'm going to shift gears, and now we're going to start talking about leg 2 of the trip, which is how we're going to travel down the road here. And at this point right here, guys, oh, my drawing isn't great. The 50 kilometers represents the entire distance there, guys, from let's see, point B here, from the hospital to this nearest point on the road. If X kilometers has been used up here, then this distance, I didn't leave myself a good place to write this, is going to be 50 minus what x is. So that is distance 2, 50 minus x. But again now, just like I did on the previous problem, we're going to use distance equals rate times time, okay, to solve this thing for t. So d2 is equal to rate 2 times time 2. And d2, we just came up with, is 50 minus x equals rate 2. That's the rate at which the vehicle can drive on the road here. That is 120 kilometers per hour. So that's going to be rate 2, oh my gosh, 120, there we go, multiplied by time 2. So dividing by that 120, time 2 is going to be 50 minus x all over 120, and there's time 2. So this first expression was telling us how much time it would take to hit the road here, and the second t expression is telling us how much longer it's going to take to, once we hit the road, to get to the hospital. So the total time right here, guys, is going to be the sum of those two individual times. Time 1, which is the square root of x squared plus 900 all over 30. And we'll add to that time 2 on the road of 50 minus x all over 120. Okay, so that expression right there, took a lot of work. That is going to tell us the total amount of time that it's going to take for the paramedics or the rescue personnel, whomever, once they pick up the hiker to get to the hospital. And that is the quantity we are trying to minimize. So with all that in mind, guys, we're going to do t prime of x. I haven't really been labeling some things, but that really is the end of step 2. Now we're on to step 3 here. Okay, equals. And we're going to do the derivative here term by term. So I've got something here to the 1/2 power. So its derivative then is going to be, let's take a look, guys. It's going to be a 1/2 times the same base, x squared plus 900, now to the negative 1/2 power, times the derivative within, which is going to be a 2x, and that still is all getting divided by 30. Gotcha. And then plus from there, all right, again, the derivative of 50 minus x over 120, we're really just doing the derivative of the top, which is going to be a negative 1, and the denominator just stays the way it was, which is going to be a 120. Right there. So that's our derivative, guys, and we're going to set that whole mess equal to 0 and try to solve that. Okay, let's see what we can do. First things first, I'm going to bring this negative term just over to the right, and then I think I've got a lot of cleaning I can do on the first term. The 1/2 and the 2 are going to cancel each other out. I think I'm just going to end up with an x on the top right there. all over 30 times the square root of x squared plus 900, all of which is now going to equal a positive 1 over 120. Okay, from there, I think I'm going to multiply both sides by the denominator of this thing. So this 30 times blah, blah, blah is going to end up going over here. 30 times the square root of x squared plus 900. And I should do the same thing right here, but I think you guys can see those are just going to cancel. So we're going to get x equals, now a 30 on top and a 120 on bottom is going to leave us a 4 right there. I think this is going to be a square root of x squared plus 900 all over 4. Let me go ahead and square both sides of this equation now. X squared is going to equal x squared plus 900 when we square the top, and when we square the bottom, just a 16. Let me multiply that 16 back over on the left. We'll get 16x squared is equal to x squared plus 900. Subtract the x squared. We'll get 15x squared is equal to 900 from there. I'm about to run out of room here, guys. And I think then we're going to get x is equal to the square root of 900 divided by 15. If I was smarter about that, that simplifies, I think. 15 goes into 96 times, so this is the square root of 60. X then ends up equaling, think man think, 4 times 15. I think that's 2 root 15 for the value there of x in that problem. And if you wanted that as a decimal, what did I say? It was just the square root of 60 right there. Shouldn't be too hard to come up with a decimal. 7.746 is what we're looking for right there. 7.746. All of that would be in kilometers. And before I box this up, I want to go back and make sure I have answered the question that they wanted. They said here, how far down the road should the vehicle aim to reach the road to minimize the time? So yeah, we were looking for the value of x here, and I do believe that's what we found here. So our answer then looks like it's going to be 7.746 kilometers from the nearest point on the road that they should aim for. Okay, so a lot of work right there, but that is problem number 20.